This is the second lecture on recursion, and in this lecture we will be covering tail recursion, non-tail recursion, which is closely related to the concept of tail recursion, indirect recursion, and finally nested recursion. In the previous lecture, we looked at what recursion is and how recursion operates on a machine level. So just to quickly recap what we spoke about in the previous lecture, we said that a recursive function or a recursive method, if we're using Java's terminology, is simply a function or a method that calls itself, and it does this in order to perform a series of repeated operations. So we said that a recursive function requires two things. We need a base case and a recursive case. And in order to decide whether the base case or the recursive case is executed, we need to have some sort of if statement. Now we said that we need at least one base case. We'll see in a moment that the base case may just simply be no operation that is performed, but the base case is then responsible for ending the recursion. So typically the base case will return a result, or it will simply perform no operation at all. We need at least one base case, but we may have multiple base cases potentially. Then secondly, we need a recursive case, and the recursive case is then a statement in which the recursive function itself is called again. Again, we said that we need at least one recursive case, but we may have multiple recursive cases. And we said then also that the important thing is that our recursive cases must then move our series of recursive calls slowly in the direction of eventually satisfying one of the base cases. If this doesn't happen, then the recursion will continue and it won't stop, so we'll have an infinite recursion in that case. So what should happen then is that all of the recursive cases should then move our series of operations closer and closer to terminating. And this is the way that you should think of recursive functions when you are writing them. Think of the base case and then also the recursive case. And again, as I previously mentioned, there may be multiple base cases and potentially multiple recursive cases as well. All right, so now that we've recapped what recursion then actually is and what a recursive function is, we'll now look at tail recursion. So tail recursion is relatively easy to define, and it's also related to non-tail recursion, which we'll discuss on the next slide. So a tail recursive function then is a function in which there is only one recursive call right at the end of the function. So in other words, the recursive call is the last operation that is performed within the recursive function. Now, very importantly, this means that no other operations can occur after the recursive call. Now, notice this terminology over here, operations. We're not talking about statements, in other words, a line of code followed by a semicolon. We're talking about an operation. So an operation may be, for example, an arithmetic operation where we, for example, add a value or multiply a value or something like that. We'll look at a situation where we don't have a situation in which no operations occur after the recursive call, and this is non-tail recursion, which we'll get to in a moment. All right, so let's illustrate then the concept of tail recursion, and we'll do this by looking at an example function over here. Here we can see we have a function which is called tail. So as the name suggests, this is then a tail recursive function. We can see that there's no return value for the tail function, and additionally we have a single parameter value, which is I, and this is an integer value. We then have an if statement over here, and we can see inside the body of the if statement we call the tail function over here. So in other words, this here will then be our recursive case. Notice then that we have no other operations that follow this if, so implicitly there's an else that is empty. And in this example, this empty else then constitutes our base case. So our base case is a situation where no operation is performed. Right, so our if statement over here then tests to see whether I is greater than 0. If it is greater than 0, we simply print I out to the screen, and then we call the tail function and we pass through a parameter which is the value of I, in other words, the current parameter value for this recursive call, and we subtract 1 from that I value, which means that we're sending through a value that has been reduced by 1. Alright, so what essentially will then happen here is that if I is some value that is larger than 0, then we will continuously print out that value and then the next smallest value and the next smallest value until eventually we reach 0, and then no operation is performed, and then all of the recursive calls would terminate. So the question here then is this a tail recursive function? Well, we can see that this is our recursive call over here. Our recursive call involves one additional operation, which is this subtraction that is performed over here. Now, we can't call the tail function unless we know what the parameter value is. So what this means then is that we perform a subtraction operation, but then the call to the tail function is the last operation that is performed. So because this call to the tail function is the last operation that is performed, that means then that the tail function in this example is in fact tail recursive. Alright, so why is tail recursion then important? Well, let's ask the question then, can we trivially replace the function, the recursive function, with a recursive call to the tail function with a loop structure? So what I'd like you to do at this point is pause the video and try to rewrite the tail function as a function that uses a loop, and this loop will then achieve exactly the same series of operations and produce the same output as the implementation of the tail function that we have here. Alright, so it turns out that it is trivial for us to convert the tail function into a loop, and over here we have a re-implementation of the tail function, but you can see that it doesn't involve any calls to tail itself. So we just simply then have a while loop. This while loop continues executing while I is greater than 0. It will stop as soon as I reaches 0. We again have an output statement here which just prints out the value of I, and then we decrement I by 1, and then the loop continues with its next test and potentially further iterations. Alright, so we can see then that we can trivially convert a tail recursive function into a loop structure. This is not to say that a non-tail recursive function can't be converted into a loop, but it is very simple for us to convert a tail recursive function into a loop structure. Right, so importantly here then, notice how the parts of the loop very clearly correspond to parts of the tail recursive function. So of course, what we can see here then is that the header or the signature of our function is exactly the same in both cases. We have a function called tail that returns nothing. It has a void return type, and it receives as a single parameter the integer value I. We can also see that in our tail recursive function over here, we have an if condition which tests whether I is greater than 0. And here in our loop implementation, we have a while loop that tests the same condition whether I is greater than 0. We also have our output statement over here, which is exactly the same in our recursive function compared to our loop implementation over here. And then at the bottom of our tail recursive function, we have a call to tail itself, and we then pass through as a parameter I with 1 subtracted from it. We again subtract 1 from I in our loop implementation, and then we just assign that to the variable I, thus decrementing it. So what this means is it's very simple to convert a tail recursive function fairly mechanically without actually even understanding what the function does into a loop implementation. We just simply transfer pieces of code and place them in a loop and make a few adjustments here and there, but essentially the translation is very trivial. It turns out that in certain programming languages, particularly functional programming languages like Lisp and Scheme, which if you continue with the third-year programming languages course, you will be introduced to as well. It turns out in these languages, you have to use recursive implementations because loops are actually not provided by purely functional programming languages. Now, and the details behind that are not that important, but the point is that you can then actually, in your compiler, implement code that will automatically detect whether a recursive function is actually tail recursive, and in that case, it can then, behind the scenes, on a machine level, it can then actually construct a loop. And it turns out then that a loop is much more efficient than a recursive function. So what I would like you to do at this point is again pause the video and try to answer for yourself why a loop is much more efficient than a recursive function. So the reason that a loop is more efficient than a recursive function is that a loop doesn't require stack frames to be allocated on the runtime stack. And we saw in the previous lecture that for every recursive call, we need to create and allocate a new stack frame. This obviously takes computational time to create the stack frame, and it also takes up memory. So it's not efficient in terms of memory space, and it's also not efficient in terms of computational steps that need to be performed. In other words, runtime efficiency. So what this means is because a while loop then doesn't have to allocate these stack frames, a while loop, or in fact any other kind of loop, will be much more efficient than any kind of recursive implementation of that loop. So in other words, it in many situations pays to have your recursive functions be tail recursive functions, because in certain programming languages these can automatically be converted into loops, and these loops will be more efficient than a recursive implementation. So now we can move on to the concept of non-tail recursion. And non-tail recursion is essentially the opposite of tail recursion. So in a non-tail recursive function or method, the recursive call is not the last operation that is performed. So in other words, there's at least one other operation that happens after the recursive call. So let's illustrate this in terms of 3 simple examples. The first example is over here, which is a function called reverse. And essentially what this function does is it reads in characters one at a time, but then once all of the characters have been entered by the user and then a new line character is reached, then this will terminate the recursion. So a new line character is reached when the user presses enter or return on the keyboard, and then all of the characters that have been entered will be printed in reverse order. So how does this thing work? Well, first of all, we need to read a single character from the keyboard. So this getChar method will read a single character from the keyboard. It will wait until a character is entered, and then once that character is entered, then it will assign that character that's been read to the variable C, which we can see is of a character type. So again, we then have an if statement, and we can see that the else portion is left out. That means implicitly there's an empty else, meaning that no operation is performed if this condition is not satisfied. So what this again then means is that we have an empty base case. In other words, the base case is that no operation is performed. Now, if we enter the body of this if statement, then we can see that we have a recursive call, namely the reverse function call over here. Following that, we then have an output statement, and this output statement simply prints out the character C. So what happens then in this case? Well, essentially what will happen is the user will type in a character, and let's assume that they've typed in the character A. So that will then be read into the variable C, and then we will print out the character, but before we do that, we perform a recursive call. So this next recursive call then will wait for another character to be entered. It's important to understand that the previous recursive call still has the character that it's read, but it hasn't printed that out yet. So then if the user types in a B character, for example, then that character will be read once again. And then before it's printed out, we then call the reverse function again. And we keep doing this until eventually the user presses enter, which means then our base case has been triggered and no operation is then performed. So now, as we've seen with all of our recursive functions, we then unwind the stack. So in other words, we go backwards through the series of recursive calls. And at each step, as the recursive call then returns, then we perform an output operation, and this prints out the value of the C variable. So in other words, the last character that was typed in will then be the first character that will be printed out. The second last character entered will be the second value printed out, and so on and so forth, until eventually the last character printed out will be the first character that was typed by the user. Now, the important thing to understand here is that we have an output statement that occurs after the recursive call over here. So what this means then is that this is an example of a non-tail recursive function, the reason being that there is one operation which is the output operation, and this is then performed after the recursive call over there. Right, so let's look at another example. This is a function called reverse Q, as you can see over here. And this function is actually very similar to the reverse function that we just looked at. The only difference is that it is using a Q data structure. So a Q data structure is essentially some kind of list-based structure. It may be implemented as a linked list, and you can insert items into one end of the queue. When you remove items from the queue, in other words, you dequeue them, that would be the terminology that we would use, then we remove items from the other end of the queue. So the opposite end to where items are inserted. So what this essentially means then is that the first item inserted into the queue will be the first item to leave the queue. The second item inserted into the queue will be the second item to leave the queue, and so on. So in other words, items leave the queue in the same order that they are inserted. So we have exactly the same setup as we had in our reverse function. We again have an if statement, so our else is then implicitly empty, which means that our base case performs no operation. And then our condition over here checks to see whether the queue is not empty. So as long as there are still items in the queue, then we will keep performing the recursive case over here. We only stop once the queue is actually then empty. So we are assuming that there are a number of items in the queue and we need to process those items. And what we want to do then is to reverse the items into another, or into the same queue itself, but we want to insert those items in reverse order. So what we do then, first of all, is we remove an item from the queue. That's what this dequeue method over here does. It removes an item from the end of the queue, and it then assigns that value to a variable called temp in this case. So then what we do is we perform our recursive call over here, which is a call to the reverse queue function itself. And then after the recursive call, we then have an in-queue operation that is performed, and that then inserts temp into the insertion end of the queue. So what then happens when we call this function? Well, what will happen then is we will remove an item from the queue, and then we perform a recursive call. So the next recursive call will again remove an item from the queue, and we'll keep doing this until we've removed all of the items from the queue. The important thing to understand is that each recursive call still then maintains the item that it has retrieved from the queue. It hasn't done anything with that yet. So what then happens is once we reach our base case, no operation then is performed. So we then unwind the stack, and we then have for each call to reverse queue, the recursive function call over here terminates. We then perform the in-queue operation over here, and we in-queue then temp, which is the value for this recursive call that has been removed for the dequeue operation over here. So what this will then mean is that the last item that was removed from the queue will be the first item that is inserted into the queue, and then the second last item to be removed from the queue will be the second item that will enter the queue, and so on and so forth. So essentially what will then happen is that the last item in the queue will then be the first item into the queue, so it will now be at the front of the queue. And after all of the recursive calls have been executed, then this will mean that our queue contains all of the same elements that were originally in the queue, but they will now be in reverse order. All right, so then just to take this back to what we were saying about tail recursive functions, we saw that tail recursive functions are very easy and in fact generally trivial to convert into a loop structure. Now, it's usually not trivial to convert a non-tail recursive function into an iterative loop. It often can be done fairly easily, but in most cases it isn't trivial. And the reason for this is that if we wanted to create an iterative implementation of a non-tail recursive function, then we often need to actually implement and create a simulation of the runtime stack ourselves. So in other words, we would need to maintain a stack data structure and then store information in that which would then be processed later. So essentially, we need to create our own simulation of the runtime stack, and this is, of course, fairly inefficient, and therefore non-tail recursive functions, because they can't be easily converted into loops and often require this explicit implementation of a stack, will then, generally speaking, be fairly slow, and we can't improve the performance of these non-tail recursive functions. Now, very important as well is situations where we have a non-tail recursive function, but the last operation isn't entirely clear. And this is definitely a question that will come up in a test or an exam on this work, so please pay attention to this. So over here we have our factorial function, exactly the same as we saw in the previous lecture. We have our base case over here, which is triggered when n reaches a value of 0, and then we return a value of 1, and that will then terminate our series of recursive calls. We have our recursive step, which is over here, and here we return n multiplied by the factorial of n minus 1. So if you would like to get more detail on how this factorial function works, then please refer to the previous lecture. Now, the important thing to understand here then, if we ask the question, what is the last operation that is performed? The answer is it isn't the recursive function. And this is even though our recursive function call over here occurs in the last statement. So what happens here then? Well, we perform a multiplication, but we can't perform a multiplication unless we know what both the left operand and the right operand are. In other words, we need to know the values that appear on the left-hand side and the right-hand side of the multiplication operator. So what this means then is we need to determine what the factorial of n minus 1 is before we can perform this multiplication operation here. And because that's the case, we need to perform the recursive call first, which means that the multiplication is then an operation that is performed after the call to the factorial function. So therefore, the recursive call is not the last operation that is performed. Rather, the multiplication operation is the last operation that is performed. So what this then means is that the factorial function is a non-tail recursive function. So far, we've only looked at recursive functions that directly call themselves. However, it is not necessary for a function to call itself directly in order for the series of operations to be recursive operations. So we may have a situation where we have one function that calls another function that calls the first function again. And this is referred to as indirect recursion rather than direct recursion. Direct recursion is a situation where we have a function that calls itself directly, and indirect recursion is where we have intermediary functions, one or more intermediary functions, which then eventually result in the first function being called again. So we may have a situation where we have a function f. F then calls function g, in other words, it invokes function g, and then function g will invoke function f again. So in other words, it passes control back to function f. So what we have here now is a circular series of calls. We have f calling g, which calls f, which may then again call g, which will call f. So we are still performing a series of recursive operations because we're returning control over and over again to this function f. However, it's not a direct recursive call because the recursive call is not actually contained in the function f itself. It's called in the function g. So this is then an example of an indirectly recursive function. So if we look at the function calls, we would have f, which calls g, which may call f, which may call g, and it can do this any number of times, but then eventually f will be called again. So f will have then an if statement within it, and the if statement will then terminate the recursion with some kind of base case, which will then stop the series of calls being performed. Okay, so a real-world example of how indirect recursion might work is if we have the internet and we have a series of links on pages, and if you follow a series of links, then they may eventually return you to the original page. So that's a sort of a concrete representation of the kind of concept that holds when indirect recursion takes place. Okay, so we may also have a series of additional intermediary functions. We may not have just a situation where we have a function f that calls g and then g calls f again, and so control gets passed along. So here we have a simple example. This is just illustrating how clothes are washed and then one wears them again and they need to be washed again in a continuous cycle. So over here we have a function called wash. Wash performs an operation on clothes. This is just an abstract operation, so we assume that clothes has some sort of appropriate data type. It's not really important for this example. And then once we've finished washing our clothes, we then iron our clothes by calling the iron function. So here we have then the iron function. Again, it receives clothes that are passed on from the call that has been performed. And once we've ironed our clothes, then we need to hang those clothes up. So we do that by calling the hang up function. And again, we pass through our clothes as a parameter. Here we then have our hang up function, and again this receives clothes which have been passed through by the previous call to hang up. And once we've hung our clothes up, then we wear our clothes, and again we pass through those same clothes as a parameter. Now finally, we have then our wear function over here, where again performs an operation on the clothes that have been passed through by the previous call. And once we've worn our clothes, we then need to wash our clothes. So we call then the wash function, passing through once again the clothes as a parameter. But notice now where we called the wash function, we then return to the first function in the set of functions. And then again, we will perform a series of calls, eventually end up at wear, and then go back again to wash. So this is then an example of indirect recursion, because we are repeatedly coming back to the wash function over and over again. However, we perform this through a whole series of function calls. So what this means then is oftentimes recursion isn't obviously recursion. We may have to trace our series of calls through a number of functions in order to determine whether the entire sequence of operations actually then constitutes a recursive operation that is performed. So we can liken this then to the standard familiar circle of life, where we have a series of stages and they all then follow on from one another and create then a cycle. Now, this cycle would not end in the real world, but generally speaking, there would at some point then be a condition that would be triggered in the wash function over here, and this would then terminate the whole sequence of calls that are performed. Now, a special example of indirect recursion is known as mutual recursion. And with mutual recursion, we have a situation where two functions call one another. So let's illustrate this in terms of a simple example, which we have over here. We have two functions. Firstly, is even at the top, and then secondly, is odd at the bottom. If we look at the headers or signatures of these two functions, we see that they're exactly the same. So both of them return a Boolean value as a result, in other words, a true or a false value, and both of them receive a single parameter value called n, and the type in both of those functions will be int for the parameter value. So we then have a series of if statements. We have an if, and then a nested if with a final else in the case of the is-even function, and the same is true in the is-odd function. We can see that we have indirect recursion in this case because the is-even function in the two recursive cases call is-odd, and then in the is-odd function we have calls to is-even. So what this then means is we have a recursive structure. If we call is-even first, then we will call is-odd, and is-odd will call is-even. And if we call is-odd first, then is-odd will call is-even, which will then call is-odd again. In either situation, we have a loop structure that's been formed, where the original function that is called is then called by the other function, which means then that we have a recursive structure, but it is indirect in nature. All right, so let's look then at the implementations of these functions. So in both cases, we have a series of if statements. We have an if with a nested if and a final else in both cases. And we can see that the first condition that is checked, where we test to see whether n is equivalent to 0, is the same in both of these functions. We can also see that there is a return in both of those cases. So what this means then is that these would be the base cases for the is even and is odd functions, because we return a value which then stops the series of calls that result in further recursion taking place. So let's look at what the outcome will be then in is even versus is odd, if this first condition here is then true in both of these cases. So in the case of is even, we return a true value, so this means then that 0 is considered an even value, and this of course makes sense in terms of the definition of even and odd values. In the case of is odd, if n is 0, then we return false, and this is because 0 is not odd, because it is considered to be an even value. Right, so then we have the nested if with its else in both cases, and here we can see again that we have the same condition in both cases, where we are comparing n to a 0 value and testing to see whether n is greater than 0 in both cases. So then we have two calls in the is even function. We have two calls to is odd, and in the is odd function we have two calls to is even. So in other words, what this means then is that we have two recursive cases in each of these functions. Now, the two recursive cases basically just deal with negative values in a different way to positive values. So if we are dealing with a positive value that is greater than 0, then in the case of is even, we will call is odd, and we will send through n with 1 subtracted from it. So in other words, we're reducing the value towards 0, which will then eventually stop our series of recursive calls. The same is true in the is odd functions. So if we are working with an n value that is greater than 0, we then call is even, and we send through as a parameter n with 1 subtracted from it. So again, we're working towards a situation where n will eventually reach a value of 0. In the case where this condition is then not satisfied in both of the functions, we will then get to the last else, and in this case for the is even function we call is odd, and we add 1 to n and send that through as a parameter. So in this case we're working with an n value that is less than 0, so the result of this will then be that our value will be increased, and that will move it then once again closer to having a 0 value, which will then terminate the series of recursive calls. Exactly the same is true in the is odd function over here, where we will call is even, and we will add 1 to n and then send that through as the parameter. And again, this deals with a situation where we have an n value that is less than 0. Alright, so let's look then at how these functions is even and is odd would interact with one another. So let's assume that we want to test whether 5 is an even value. Now at this point I'd just like to say that we wouldn't actually in a real world setting perform this kind of recursive test to determine whether a value is even or conversely odd. There are much simpler ways of doing this by means of just simple mod operations. So this recursive implementation is very inefficient. It uses a lot of memory and also a lot of computational resources, and this is for the same reasons that we've discussed previously, because we have this runtime stack on which allocations of stack frames need to take place. So please don't ever implement a test for an even or an odd value in this way. This is just intended to illustrate indirect recursion, specifically mutual recursion. So let's see what then happens if we perform a call such as if is even over here and we pass through a parameter value of 5. So we're testing to see whether 5 is an even value. Now, of course, we can very easily see that 5 is an odd value. In other words, it's not an even value. But if we look at our series of calls, we will then have is even, which is called first. So this is by the user code. Using the is even and is odd functions, we call is even first with a parameter value of 5. This will then result in the recursive case being triggered triggered, which we'll then call is odd, with a value 1 less than n's original value, so we will pass through a value of 4. Is odd will then call is even with a value of 3. Is even will then call is odd with a parameter value of 2. This will result in a call to is even with a parameter value of 1, and eventually we will then call is odd with a parameter value of 0. So now we've reached our base case, and this is now in the is odd function over here. We've reached a situation where n is now in fact 0, and therefore we will return false. So what this means then is our series of calls over here have resulted in finally an is odd call with a parameter of 0. That results in a false result, a false return, and that will then be returned backwards through the series of recursive calls that we've performed until eventually we reach the original is even that was called, and that will then return false. So that will give us then a false result, indicating correctly that 5 is not even. So now let's look at a converse situation where we call is odd first. So again, we're going to use a parameter value of 5, but now we're calling is odd to determine whether 5 is in fact an odd value. Now, of course, we can very easily see that 5 is an odd value, but if we look at the series of calls that are performed, we again have this oscillation back and forth between is odd and is even back to is odd again. So we initially then call is odd, we send through a parameter value of 5, which will then call is even with a parameter value of 1 less than 5, in other words 4. Is even then calls is odd with a parameter value of 3, because that's the result of subtracting 1 from the previous n value, which was 4. Is odd then calls is even, and we send through a parameter value of 2. Is even then calls is odd, and a parameter value of 1 is sent through, and then finally is even is called, which sends through then a parameter value of 0. If we look at is even, when we have a situation where n is in fact 0, we then have a base case where we then return true, and therefore the true result is then produced by the final call to is even, which is then sent back through all of the returning stack frames that are allocated one by one until eventually we reach then the first is odd that was called, and that will then produce a result of true, indicating that 5 is in fact odd. So essentially what we've done is we've triggered a situation where we have a series of calls back and forth, but the final call then is an is even check on a value of 0, and because 0 is then considered an even value, that will then produce a true result, which will then give us the correct final answer. Now, the important thing to understand here is that we have a situation where we have mutual recursion, and the reason that this is called mutual recursion is because the base cases are equally important for all types of recursion. So if we look at these two example calls that we had here, we can see that we reached in the first example the base case of is odd, and in the second example we reached the base case of is even. The point is both of those base cases are required in order for the original calls either to is even or is odd to work correctly and the series of recursive calls to then actually terminate. So what this means then is that these two functions, is even and is odd in this case, are mutually dependent on each other. In other words, is even depends on the base case of is odd, and is odd depends on the base case for is even. And this is what makes these two functions then mutually recursive, because they exist on an equal footing with one another because of the fact that they rely on each other's base cases. The final topic that we'll look at in this lecture is nested recursion. So in the case of nested recursion, we then have a situation where we have a recursive function call. However, at least one of the parameters of this recursive function call will then also be a recursive function call. So let's look at this in terms of this example implementation over here of a function called nested. And it's not really important what the nested function computes. It's basically just modeling a complex mathematical function. So the point is that the nested function returns an integer value, which is its result that it computes, and has a single parameter value called I, which is also an integer. Now we have two base cases over here. So the first one is tested by this if statement over here, and then the second one is tested by this nested if statement, and then we have one recursive case over here on the last line of our function. So the first base case, we do a test to see whether I is 0, and if I is 0, then we return a value of 0. And of course, because we're returning a value directly, we're not performing any further recursive calls, which means that we then terminate a series of recursive calls, resulting then in the stack unwinding. Now, if this condition is not satisfied, we then move on to a second condition, which checks to see whether I is greater than 4. And if I is greater than 4, then we return the value of I, which is our parameter that we've sent to this call of the nested function. Once again, we're just directly returning a single value, so this will once again terminate a series of recursive calls. So far so good. There's nothing particularly interesting that we've seen so far. But now if we move on to the single recursive case over here, we can see that we return a value. And this value is the value that's returned by this call to the nested function. Now we can see we also need then a parameter for this call to the nested function, and this is then produced by an arithmetic expression over here which involves addition and multiplication, but very importantly it also then incorporates another call to the nested function over here, which then also has a parameter value computed and sent through as a parameter. So here we then have a situation where we have a recursive call in which one of the parameters, there is only one parameter in this case to worry about, so the single parameter then is computed using the result of another recursive call. So this is then referred to as nested recursion because we have a second call to the nested function which is embedded in one of the parameters of the first call to the nested function. So what's important to understand with nested recursion is that it is very complex. This is because it involves a large number of recursive calls and in fact almost like split branches of recursion that occur throughout execution. So in other words, there's a lot of recursion, which means we have a lot of stack frames that are allocated on the runtime stack. We know obviously that that uses a lot of memory. We may in fact run out of memory in particularly bad situations. And we also use a lot of computational time because we have to take time to allocate those stack frames. So in other words, nested recursion is both memory inefficient and also execution inefficient. Alright, so what I would like you to do at this point is pause the video again and try to determine what the output would be if we call the nested function with a parameter value firstly of 1, then of 2, then of 3, and then of 4. So work that out. If you need to, you can actually implement the nested function, and you can actually then add debugging output to see when the nested calls are taking place and what steps are actually performed. Alright, so let's look at our nested function, how this will actually execute for two of the parameter values that I gave you on the previous slide. We'll leave the remaining two as exercises for you to work out yourself. Alright, so down here we have the implementation of our nested function, just simply to be able to keep track of whether a base case or a recursive case is being executed. So we'll assume then in the first case that we call nested with a parameter value of 1, and we see then that 1 is not equivalent to 0 and it's also not greater than 4. So that means we need to then perform our recursive case over here. So this results then in a call to nested, and this is the parameter that's sent through. So we have 2 plus 2 multiplied by nested with a parameter of 2 multiplied by I sent through, and I of course in this case is 1, so that is the value that's substituted there. Now before we can determine what the result of this call to nested is, we need to execute this recursive call over here. So we are calling nested with a parameter value of 2 because that's the result of multiplying 2 by 1. So now we perform another call to nested. We're passing through a parameter value of 2, and we see that 2 is not equal to 0, and it's also not greater than 4. So once again, we then have our recursive case that needs to be executed. So here we have then our call that is performed. We again have 2 plus 2 multiplied by, and then a call to nested where we pass through a parameter value of 2 multiplied by I. Because I's value that we sent through on this call is 2 multiplied by 1, in other words a value of 2, we then pass through as the parameter to this nested call over here 2 multiplied by 2 in that case, in other words 4. So again, we then need to perform a call to the nested function up here. We're passing through a parameter value of 4, and we see that 4 is not equivalent to 0, and it's also not greater than 4. So once again, we need to perform our recursive step over here. So that's exactly what we perform here. Again, we have 2 plus 2 multiplied by, and then a call to the nested function itself. We are passing through 2 multiplied by I, and I's value that we sent through is 2 multiplied by 2, so that is 4 over there. So again, we can't compute the return of this call to nested. We need to first of all look at this second call to nested over here. So now we are calling nested with a parameter value of 2 multiplied by 4, in other words 8. And if we look through our tests, we see 8 is not equivalent to 0, but it is greater than 4. So now we can return I's current value. So what this means is we are returning I's value here, which we've computed as 8, and that is the result that is then returned. So now we multiply 8 by 2, and then we add 2 to that, and you can check my calculation. The result of that computation is then 18, which is then returned by this call to nested over here. So now we have a result of 18 for this call. So we can again then multiply 18 by 2 and then add 2 to that. And again, you can check my calculation. The result of that is 38. So now we have a result for this nested call to nested over here, which is then 38. Again, we multiply that by 2 and we add 2 to that. And that gives us then a result of 78, which is then the result of our original call to nested with a parameter value of 1. So now let's look at a second example over here. Let's look at a call to nested with a parameter value of 3. So again, we see then that our parameter value of 3 is not equivalent to 0. It's also not greater than 4. So this means we then enter our recursive case over here. So we are then calling nested, and we're passing through a parameter that is computed as 2 plus 2 multiplied by a recursive call to nested, where the parameter is 2 multiplied by I. We saw that the I value that's been passed through is 3, so we're calling nested with the parameter value that is computed as 2 multiplied by 3, in other words, 6. So now we need to determine which one of the cases will then be triggered by this call to nested. We're passing through a parameter value of 6. 6 is not equivalent to 0, however it is greater than 4, which means we've now hit a base case, and we then simply return i's value. So i's value we computed as 6, which means we then have a result of 6 which is returned. So 6 is then multiplied by 2, and then we add 2 to that, and the result of that then is 14, which we then return as the result of our original call to nested. Right, so the important thing here then is that we can see in certain situations that we have a whole series of calls to nested, and we have other situations where there are very few calls. So in general, any recursive implementation, but in particular very often nested recursion implementations have unpredictable results, where with certain parameter values we'll have very few recursive steps that are performed, and in other cases we have a large number of recursive calls that are performed. Now, the previous example of nested recursion wasn't too bad in terms of computational complexity and the amount of memory that would be used for the recursive calls. However, I did previously mention that in some examples of nested recursion, we may have a situation where our implementation will be very computationally expensive and also will use a lot of memory. And the reason for this is that with nested recursion, we may have a large number of recursive calls that could take place. And of course, we need to then allocate a stack frame each time that we perform a recursive call. So this allocation takes up computational time, and also because the stack frame needs to be allocated on the runtime stack, it uses up memory. We may even run into a situation where we run out of memory, and in this case, our program would then terminate in some way. It would either crash or it would generate some kind of error. Now, in the case of Java, what happens is we get an error that is generated, and this is referred to as a stack overflow error. It's not possible to recover from this error, so essentially what will happen is our recursive function will execute for a very long time. It might produce a lot of output, but then eventually it will terminate and it will indicate that a stack overflow error has occurred. In this case, what it then means is we've run out of memory because we have too many function calls that are active. So in other words, our recursion has gone too deep and we don't have memory to perform further recursive function calls. Right, so then the question that arises is how bad can nested recursion get in terms of time, in other words, execution time, and space, in other words, memory space efficiency. So in order to illustrate this, we're going to look at a very famous function called the Ackermann function. Now, in terms of what the Ackermann function specifically is and what it demonstrates, this is somewhat beyond the scope of this course. So for our purposes, all you really need to know about the Ackermann function is that it is a recursive function that generates a lot of recursive calls, and we would say that this is a very deep recursion that takes place. There are other properties associated with the Ackermann function, but we are not interested in that in the current context. So over here we have a Java implementation of the Ackermann function. The function is called Acker. It produces an integer result, which is the final result of the function. And the function is then applied for two parameters. So we have both parameters being integer values. The first parameter is called I, and the second parameter is called J. So then we have the implementation of our Ackermann function over here. We can see that we have a base case over here that just returns a value, and then we have two recursive cases over here. Now what's important to note is that in this second recursive case at the bottom here, we have a call to the Acker function itself, but we can see then that we send through just a regular integer value that is computed for the first parameter I, but for the second parameter j, we have a call to the Acker function itself. So in other words, we once again have a situation where we have a recursive call where at least one of the parameters is also a recursive call to the same function. Alright, so let's look at how this would execute with very simple parameter values. So we're going to assume that we call the Acker function where the first parameter for I will then have a value of 1, and the second parameter j has a value of 2. So what happens then in this case? Well, we need to test our conditions. So first of all, we test to see whether I is 0, and of course it isn't because I's value is 1 in this case. So we then haven't hit this base case over here. We get to our second condition check over here, and we test to see whether I is greater than 0. Well, it is because it has a value of 1, but our second parameter value j has a value of 2, meaning that it isn't equivalent to 0, which means that this second condition then fails as well. So now we've moved on to this last recursive case over here, and we need to then perform a call to the Acker function. So we can compute the first parameter quite easily. We just subtract 1 from I because I's value is 1 there. This first parameter will then be computed as 0, which we see over here. However, we need to then perform another call to the Acker function, so we don't know what the result of this will be. So we therefore have a recursive call that has to take place. Well, we pass through then I's current value as the first parameter, and we saw that that was 1. So we have then a recursive call where the first parameter is 1 once again, and then the second parameter we take j's current value and subtract 1 from that. So j's current value is 2. We subtract 1 from that, giving us a result of 1. So for the next call to the Acker function, we then have a second parameter value of 1. Right, so again, what we then need to do is test our conditions. We again see that I is not equivalent to 0, so we haven't triggered a base case yet. We also see that I's value is 1, which is greater than 0. However, J's value is 1, and that is not equivalent to 0, which means once again we are triggering the last recursive case over here. So again, we need to then call the Acker function, and again we can compute the first parameter quite easily. So we take I's value and subtract 1 from that, and that gives us a result of 0 over there. Our second parameter, however, we don't know what the value is yet at this point, so we need to again call this Acker function, and once again we pass through I's current value as the first parameter, so I's current value is 1, and that is passed through as the first parameter for the third call to the Acker function. We then compute the second parameter value, which is then j with 1 subtracted from it. Because j's current value is 1, we subtract 1 from that, and therefore the parameter for this call to the Acker function is then 0. Right, so what happens then at this point? Well, again, we need to then check our conditions. We see once again that I does not have a value of 0, so we don't have then a base case situation. However, what we do see here then is that I, which has a value of 1, is greater than 0, and also we see that j's value for this call is 0, and that satisfies then the second part of the second condition. So in this case, we've now triggered this recursive case over here. So what we then do is we call the ACCA function. You can see we're not performing nested recursion in this case because we just simply compute our parameter values directly. So for the first parameter, we then take I and we subtract 1 from that. Because I's current value is 1, that means we have a parameter value of 0, and then we pass through as the second parameter value simply 1 over there. So now we've got another call to the ACCA function. We then need to test our conditions once again, and we see that the first test is for I, the first parameter, which is tested against 0, and we see that I's value is 0 here, so now we simply return a value which is j plus 1. So this will then result in this call to the ACCA function returning a value of j plus 1, which is then 1 plus 1, which is then a value of 2. So now we have a result for this second parameter of the ACCA function over here. So again, we then need to determine what the result of this call to the ACCA function will be. So once again, we need to then test our conditions, and again we see that I is equivalent to 0 because the first parameter is 0 for this call, which then again means that we have now reached a base case. So again, we then compute j plus 1 and we return that. Well, j's value here is then 2, so that means we will then return a value of 3, and so we have a value for our second parameter for this call to the ACCA function. So again, we need to then test our conditions, and we see once again that the first condition is satisfied because I, the first parameter value, is 0, and therefore we return j plus 1. J's value is 3, so therefore the result that is returned is then 4, as we see over there. Alright, so for these parameter values then, in other words, an I value of 1 and a j value of 2, we see that there aren't too many recursive calls. But we can see that with different parameter values, we can have a large number of recursive calls that will continue further in that direction. And also, we were very lucky in this case that our I parameter value was 1, because this means then very quickly we reach a call in each case where the ACCA function has then a parameter value of 0 in that case. So in other words, what this means is then we will very quickly reach our base case. But if I's value was not 1 in this case, then each of these calls to the ACCA function could result in further calls. And these could be a large number of calls, which then of course means there will be even more recursive calls that will take place. So what we can see then intuitively at this point is that for different values of I and j, there will be potentially a very large number of recursive calls that could be performed. So let's look at a situation then where we call our Ackermann function with an I parameter of 3 and a j parameter of 2. So what happens in this case? Well, I'm not going to run through all of the recursive calls because it does get quite involved, but essentially what we are interested in is the depth of the recursion. So in other words, what will be the largest number of recursive calls that need to be performed before we reach a base case and then finally return a value. So it turns out in this case that we have a depth of recursion of 31 in this case. And all we've really done here is we've upped the value of I from 1 to 3, and we've kept the j value constant at 2 compared to our original example. So we can see that we have a large number of levels of recursion that are performed here just with a very simple increase of 2 to the I parameters value. So let's now look at another call here. Here we are again calling the ACCA function, and we are passing through a first parameter value, in other words, i's value of 4, so we're increasing that even further. And again, we are just passing through a value of 2 for our j parameter. Now, it turns out it would be completely impossible for us to determine how many levels there are to this recursion by means of actually tracing the series of recursive calls, because there are so many of them. And in fact, the depth of the recursion for this call would exceed the number of atoms in the universe. So essentially, that call would run out of stack space, and even if you had a very large amount of memory, it would eventually run out of stack space. And even if you had infinite memory, you would still have a large number of recursive calls that would have to be performed, and therefore we would still have a very, very long execution time. So this is an example of a situation where nested recursion results in so many recursive calls that we very quickly will run out of stack space, we'll run out of resources, and then our recursive function call will simply terminate with an error. Alright, so that concludes then our discussion for this lecture. In the next lecture, we'll cover the last 2 sections on recursion, and there we'll be looking at excessive recursion and then some fairly interesting examples of recursive calls, which we refer to as backtracking.